You're going to get it today, as far as I know, later on from Stephen in his lecture this afternoon. So it's a set of problems, mathematical problems that you have to do the solutions of and submit them. I'll talk to you in detail about my questions when I see you in next week's lecture. But it's based on the stuff we've been doing up to now and the things we're going to do today as well. Okay, so just all concept of partial differentiation, the applications of it, and the associated concepts that we've looked at up to now. Okay, we've got quite a few weeks to do it. It's due less than 0. Should say here when it's due. I think it's 0 because I'm not a student. Let's see if it says something now. It says it's 2. So it's due on the 7th of December. Okay, so a fair bit of time to do it. Okay, but so you'll get it later today. Stephen will introduce it to you, but I'd encourage you to begin work on it straight away, immediately. Get to know all the questions on it immediately. Realize what questions are straightforward, what questions are slightly harder, and so on. Don't put it at the back of a drawer or something and postpone it. Okay? Do engage with it fully straight away. Okay. Okay then. But that's to come later today, and as I say, I'll give some kind of commentary on questions from my half on it when I see you next week. Just to let you know, I've begun releasing the solutions to my tutorial questions. So if you come down a little bit from the head of the page, you'll see here I've got the solutions to exercises 1.1 and 1.2, that first batch, and I'll probably release the other ones to the next couple of batches, 1.3 and 1.4. I'll release those fairly soon as well, probably at the end of this week. Then, as we go through the course, you'll see appearing here the various solution files for those exercises in the notes. Okay. So, any questions before we continue? Everybody happy? Okay. So last time we were looking at the chain rule. The chain rule, remember, told us how to work out derivatives of a given function when we change the coordinate system for the space, or change the set of variables that we're using to represent points in the domain of the function. Okay. So for a function of two variables, it's summarized here in definition 1.5. So f might be a function of two variables, x and y, and it's telling you what the third coordinate, or just what the value of the function is. But here, if we imagine switching to an alternative system of coordinates, here called s and t, for that domain, then these equations here tell us what the derivatives of f will be with respect to the new pair of variables s and t. And the ingredients, in the recipe, if you like, are the derivatives of the function with respect to the old variables x and y, and the derivatives of x with respect to s and y with respect to s, x with respect to t, y with respect to t. So those are the derivatives of the transformation functions. They're represented as u and v. Okay, so this is what we discussed last week. That's what it looks like for a case for a function of two variables. It can be generalized to functions of any number of variables, as it is here in the second part of the definition 1.6. So you got a set of n old coordinates, say, and you're moving to a set of n new coordinates, s1 up through sn. You've got transformation functions ui, which tell you what the ith x coordinate is in terms of the new coordinates. And then you've got n of these chain rule equations. Okay, they're indexed by I, so you got one of these equations for each value of I, and it's telling you what the derivative of the function is with respect to the ith new variable. And it involves the derivatives of the function with respect to all of the olds, because you're summing over j here. J is the subscript on the derivative with respect to xj. And you're also taking the derivative of the transformation function uj, which tells you what xj is in terms of all the s's. So you're looking at all those transformation functions and taking the derivative of each of them with respect to the ith new variable SR. Okay? So this is just the straight generalization of the two variable case. Okay, we had a whole bunch of exercises on that, and some of those exercises can inform next week's or this week's tutorial for you as well. So this set of exercises here in 1.3, various exercises on chain rule there. And there was also an extra set of problems, I believe, if I recall correctly. Yeah, further problems on the multivariable chain rule and Jacobians. So you can get that from the Moodle page as well. I don't have typed up solutions to these, but we did some of them in the tutorials and in the lecture. It's just further problems for you to practice with. And there's a few notes at the top of that about other resources, which are some of the recommended textbooks for the course. Okay, so we're going to move on now and look at another couple of applications of partial differentiation. And these will feature in the, as you'll see later on today, these will feature in the coursework. And they can both, so what we're doing today is a Taylor series for functions of two variables, and also stationary points for functions of two variables. They can both be seen as the generalizations of equivalent properties for one variable functions. Okay? So the first one we're going to look at is the Taylor series. Now, you should be familiar with the concept of Taylor series from your studies. From your studies last year. So for a single variable function, maybe I'll just do this on the other side actually. So for a single variable function, Taylor series for a function f of x about the point 0 should I make this general? I'll make it general, f of a. This is what it looked like. So this was a rule for evaluating, excuse me, for evaluating the function at a nearby point to some base point a. It was an infinite series. It was an infinite series that was a polynomial in this variation h. So it was h to the n over n factorial. And then there were these other, so the 1 over n factorial is part of the coefficient of h to the power n. And then there were these other factors in the coefficient, which was the, sorry, I'm summing over j. So yeah, let's change that to n. So summing over n equals 0 to infinity. H to the power n over n factorial, and we're taking the nth derivative of a evaluated at the base point a. Okay. So the beginning of that would look like the value f of a, that's when n is 0. When n was 1, it would be the first derivative of f at a times h. Then it would be the second derivative of f evaluated at a over 2, which is 2 factorial times h squared, and so on. Third derivative evaluated at a over 6 times h cubed, and so on. Okay. It was an infinite polynomial series in the quantity h, which express the value of the function f at this nearby h. Okay? And it depends on all the derivatives of f, all of them evaluated at the base point. And the idea is that the most important part of the approximation is the very first term. So, like in general, for a small variation h, the value of the function at the nearby point will be approximately the value it had at a. That's the main part of the approximation. Then you have a linear approximation. That's the constant approximation. Then you have a linear part to the approximation, which is basically just the approximation provided by the tangent line. Because the first derivative of f evaluated as the gradient of the tangent line, and multiplying that by the quantity h, that is basically just approximating the function by the value that lies on the tangent line corresponding to the point a plus h in the domain. Then you can add on these finer and finer corrections based on higher and higher derivatives of the function. So in principle, if you take any finite part of this Taylor series, you might refer to that as a Taylor polynomial. So any finite chunk at the beginning of this will be an approximation to the value of the function of the nearby point. And that approximation can be made better and better by taking in more and more terms of the Taylor series. So that's what we looked at last term for functions of a single variable. Now we want to do the same thing, but for functions of two variables. Okay? So can we do this? Can we do this for functions of two variables? Functions of two variables. There's some f of x, y. The kind of thing we're going to expect is some way of evaluating the function close to a base point. So the notation that we're going to use h for the variation in the x-coordinate and k for the variation in the y-coordinate. So we're thinking of the point AB as being some fixed base point. And well, what kind of thing do we expect here? I mean, we'll see exactly what it is now shortly. But we'll expect some similar thing to this. Okay? So what we'll expect here is some kind of expression involving, it's going to be a sum over all the indices j. These are things just kind of floating around here, k to the j, but maybe it will have products as well, h squared, k cubed, and so on. Just got all these elements floating around. So we're going to have lots of polynomial terms in h and k. These are just floating around, just kind of ingredients we might expect to be in here. And we'll also expect partial derivatives, df dx, df dy, and higher order derivatives, so taking jth derivatives. So some kind of summation process that does the same thing as in the single variable case, but for the two variable case. So you've got, we'll expect to see a polynomial in the two variables h and k, which will have powers of h, powers of k, but also products of powers, and we'll expect to see the various partial derivatives as well. Okay, so don't worry about taking that down exactly. I just want to indicate the elements we might expect to see floating around. Okay, just polynomial terms in h and k, and the derivatives of the function. So let's meet it precisely now in the notes. Okay, so this is what it looks like. Now, the way we formulate it is we make use of this differential operator d. Okay? So we got our function f of x, y. We've got our base point a, b. So we're considering f evaluated at the nearby point a plus h, b plus k. And in order to formulate the Taylor series, we make use of this differential operator, which is h d dx plus k d dy. Okay? So h times the derivative with respect to the x variable, and h is the variation in the x coordinate, plus k times the derivative with respect to the y variable. Okay? k is the variation in the y coordinate. And this is a differential operator. Okay. It's something that you apply to a function. It doesn't have a value on its own, because it's assembled out of h times the operation of differentiating with respect to x, plus k times the operation of differentiating with respect to y. It's something that you take a function and you hit it with d. When you hit a function f with d, it produces the combination h df dx plus k df dy. And that's something more familiar to us. It's a combination of the derivatives of f with respect to x and y, okay? Multiplied by these variations h and k. And this kind of thing we might evaluate. This kind of thing, you see these expressions df dx and df dy, those will be functions of x and y. And this kind of thing we might evaluate at the base point a and b. Okay? That's what we're going to see here. You could put some kind of subscripts here, d, a, b, applied to f. It's forming this combination and evaluating it at the base point. So evaluating it at the base point means putting these values a and b for x and y into the two partial derivative expressions. Okay? Not into h or k. H and k are the variations of the base point. Okay, that's the operator d. Now we're also going to talk about higher powers of the operator as well. Now higher powers of the operator, so they'll appear as d raised to some power, and they refer to, so what is d to the power n applied to f going to be? Well, this is going to be d of, etc., and eventually it's d of f here. So there's n d operators here. So it's a composition applying the operator d to the function n times. Okay? D applied to D, applied to D, and eventually in the middle there's a D applied to F. Then you apply D to that, and D to that, etc. Now it shows you here what the second order one looks like, D2F looks like. The D2F is D applied to D of H, sorry, D applied to D of F. So here's one copy of D, and here's d of f. Now we already know what d applied to f is. It's h df dx plus k df dy. And then you're applying d to the result. So you're applying this see this bracket here on the left, in the middle line, this bracket on the left is a differential operator that's applying to the one on the right. So the first operator applies to both, the second operator applies to both, and you see what you have. When you expand it out, see there's a coefficient of h in each one, so you pick up a h squared, then you pick up d dx of df dx. But d dx of df dx is just the second derivative, d2f dx squared. Similarly, you get a k squared d2f dy squared term, and then this mixed term, so this comes about from taking the d dx of the df dy and the d dy of the df dx. Remember, by Clairaut's theorem, those two mixed partial order derivatives, d dx of df dy and d dy of df dx, they're both the same. They're both equal to this d2f dx dy term. But there's two of them, and each is h times a k times a h. So we got 2hk times the mixed second order derivative d2f dx dy. Similarly, you could write down expressions for d cubed f, d to the power 4f, and so on. And so Taylor's theorem for functions of two variables is this result here. So this is the required. So that thing I grew in the green cloud there. This is the precise value of it, and it very much mirrors the. It's pretty. I've rubbed it off already, but it very much mirrors the single variable case. So the Taylor series is the sum over the index n from 0 to infinity. Again, we have this 1 over n factorial term. And we have the nth iterate of the operator d applied to f and evaluated at a and b. Now the polynomial terms in the variables h and k, those are inside all these powers of d. The d applied to f term had order 1 polynomial terms, h and k there. The d2f had all the order 2 terms, which are h squared, k squared, and h times k. Okay. Inside the d cubed term, you will find h cubed, k cubed, hk squared, kh squared. Those 4 order 3 polynomial terms in h and k. Remember, the order of a multivariable polynomial term is the total sum of the indices. When you're talking order 3, you expect to see h cubed, k cubed, hk squared, and kh squared. All the combinations, the product combinations of k and h, where the total sum of the indices is 3. Okay. We can expand that out. It's the function f evaluated at the base point. It's the first iterate of d applied to f evaluated at the base point. So this evaluation of the base point AB, the AB goes in for x and y into the partial derivatives. The h's and k's stay there as their polynomial terms. We don't replace anything for them because they are the variables of this expression. A and B is the fixed base point. H and k are the variables here. So inside these d to the power n terms, we have the polynomial terms in h and k. And again, it works similar to the Taylor series for functions of a single variable, in that if you take any finite initial part of that infinite sum, you get a pretty good approximation to the value of the function. The more and more terms you take in, the better and better the approximation becomes. So let's look at an example of this. So there's a prepared example here, example 1.11. So the function we're going to work with is this combination of sine and cosine. Sine of x plus 3y, cosine of 3x plus y. And we're working on the base point pi over 2, 0. So these are the values of a and b here. A is pi over 2 and b is 0. So it's asking for the Taylor expansion of order 2. So that means we'll have to work out the value of the function at the base point. That's d to the power 0. We'll need the order 1 term, which is d applied to f. And we'll need the order 2 term, which is d squared applied to f. Well, evaluating the function at this base point just gives the quantity 1. That comes about from the sine of pi over 2. Isn't that right? Sine of 1, 2. Yeah, sine of pi over 2 is 1. Cosine of 3 pi over 2 is 0. So we just get a value 1 for the constant value of the function. We can then look at partial derivatives. So the partial derivative of f with respect to x and the partial derivative of f with respect to y. Maybe we just got the values there of those evaluated at the base point, pi over 2 and 0. But they come out as 3 and 1. df dx will, of course, be cosine of x plus 3y minus 3 times the sine of 3x plus y. Okay. Evaluating that at the base point pi over 2, 0 gives us the quantity 3. And similarly, evaluating the y derivative at pi over 2, 0 gives us 1. And so the first, the order 1 term then from the Taylor series, this df applied to evaluated at pi over 2 and 0, this gives us the quantity 3h plus h. Okay? So this 3 here is the coefficient of h, the 1 is the coefficient of k. We've got h times df dx plus k times df dy. Similarly, we can go for the order 2 term there. So there's 3 partial derivatives to work out. You need the x derivative twice, the y derivative twice, and then the mixed second order one. Once with respect to x, once with respect to y. The evaluations we find there, minus 1, minus 3, and minus 9. So the term d2f evaluated at pi over 2, 0, this gives us the quantity minus h squared minus 6hk plus 9k squared. So these coefficients, the minus 1 in front of the h, the minus 3 in front of the, well, it's the minus 3 multiplied by 2 in front of the hk. Because remember, in front of the hk, we have the 2 times hk, and then the -9 in front of the k-square. Of course, when they appear into the Taylor series formula, then we also have the 1 over n factorial terms as well. Okay. So then at the bottom, then you can assemble what would be known as here as the order 2 Taylor polynomial approximation for our original function. It's the values of the function at a nearby point to the base point pi over 2, 0. So the coordinates here are pi over 2 plus h and k, which is 0 plus k. 0 is the y coordinate of the base point. Okay. So that's a useful device for us, okay? It enables us to take, as long as they're nice, well-behaved functions, functions that have partial derivatives, functions that are continuous, they're not too wild, but it will allow us to approximate them as closely as we need by using simple polynomial functions, okay? Simple polynomial functions are very easy to understand, they're very easy to integrate, to differentiate, and so on. And so being able to approximate our arbitrary functions with those is very good. And of course, computers can evaluate, remember, fundamentally computers are kind of stupid. All they can do is add numbers together, and by extension, multiply numbers together. But as long as you can add and multiply, you can evaluate polynomials. Okay? So that is where basically the way we numerically evaluate arbitrary functions is via their Taylor series approximations or closely related similar types of approximations using basic functions, okay, such as the polynomials. Okay, so that's one application. Then the last application of the derivative that we're going to look at before we move on to integration is to look at stationary points. So again, this can be seen as a generalization of a familiar situation in the single variable case. And the single variable case, in the single variable case, we had the situation that you've got a function of a single variable. There's this graphical object of it, which is the graph of the function. So this can be the graph of y equals f of x. You have your x coordinate, your single variable for the function. You add in a second coordinate, make a 2D plane out of them, and then the function determines this, there's this graphical object associated to the function, which is the graph of the function. And there are these special points on the graph. These local minimums, local maximums, and if I draw one, these points of inflection. Maybe let's draw one here. An inflection point. These are the three types of stationary point. Three types of stationary point for a function of a single variable. They're the three types of situation where you've got a horizontal tangent line to the function. That horizontal tangent line is, of course, the locations where df dx, where the partial derivative is equal to 0. Okay? So the places where the function is momentarily stationary. It's acting momentarily like a constant function. Its linear first-order approximation is just a flat horizontal line, namely the tangent line. Okay? So just as in Taylor series, we are interested to know what's the equivalent story for functions of two variables. Well, functions of two variables, we have an f of xy. The equivalent thing to the graph of the function is the surface defined by the function. That's where we have this third variable z, it takes the values of the function, evaluated at a base point x, y. So you've got this base plane, y plane, which you can think of as the floor. The xy plane is the floor, and the z coordinate would be this vertical line up between the two walls, z coordinate here. And the similar thing to the graph is we get this surface. Okay, we get the surface with the function. The surface defined by z equals f of x1. Now this surface also has a tangent structure. It's not tangent lines, now it's tangent planes, okay, which we discussed a few lectures ago. But again, these tangent planes can sometimes be horizontal, okay, can sometimes be flat. So what are known as stationary points of a function of two variables. The definition of a stationary point, AB, is one where the two partial derivatives of the function, when you evaluate them at the base point AB, where they both give you the value 0. Okay, these will be locations where the tangent plane is at this flat plane. These will be locations where the tangent plane is flat. Okay. Now, what do these look like? If you have this intuitive idea of what a local maximum, local minimum, and inflection point look like, what are the possible structures we can see on the surface of a function of two variables? Well, we'll hopefully look at some examples on a computer shortly. But they come in three types again. Now, they're slightly harder to give nice, convincing drawings of, but we'll look at some computer plots now shortly. We could have local maximums, which are like the points at the top of a hill. Okay, so this surface structure could have a point on it, which is like the point you have at the top of the hill. Okay? Locally, in a small neighborhood of it, it's the highest point around. And all the other points are at lower altitude. Okay? So you can have these local maximums. Similarly, you can have local minimums, which are like points at the bottom of a depression. So this is, we have our whole 2D surface here. Maybe I'm just looking at a cross section of it. So you can imagine this kind of sheet, the surface, the undulating sheet here. It could be the opposite of a hill, basically. A point on the surface where, in a local neighborhood at that point, all the other points on the surface are at a higher altitude. Okay? So the point at the bottom of a depression. There is a third kind of point, and it's more or less the generalization of this inflection point from one variable. And this is what's called a saddle point. And it's called a saddle point because its shape is supposedly reminiscent of a horse's saddle, or what the horse's back looks like. So that's the underside of the surface there. Here is the saddle point. If you imagine a horse's saddle, the place where you sit, you see there's two things going on with the horse's saddle. Forward, if you're sitting on the horse, forward and back from you, the horse's back, it goes up, and the saddle even more so comes up in front of you and up behind you to keep you stable on the horse. So if you look forwards and backwards, the saddle point is like a local minimum. Because forward and backwards, from the center point of the saddle, it's acting like a local minimum. But of course, your legs go either side over the horse, so the saddle point is also, in some ways, a local maximum. If you go off to the left or to the right, the point on the saddle, the center point of the saddle, is the high point, isn't it? Okay? So your legs come off here, front of the horse is either here or here. Sure. So you get this point. It's a mixture of a local minimum and a local maximum. In one direction, the point is behaving like a local minimum. In the other direction, it's behaving like a local maximum. So it's kind of a half a maximum, half a minimum. Now, remember in the one variable case, these points were found by looking for zeros of the derivative. For stationary points of two variable functions, it's the same thing. You're looking for simultaneous zeros of the two first order partial derivatives. So they both have, at some point A, B, both these partial derivatives have to vanish. They both have to be zero. There was a way of classifying these one variable ones. The local maximum had the property that the second derivative, df2 dx squared, was negative at the local maximum, was positive at the local minimum, and it was equal to 0 at the inflection point. And there's a similar story here for how to classify the three types of stationary point for surfaces, function, the graph of a two-variable function. Okay? So this is again classified by second-order derivatives. Okay, but well, there's only one second-order derivative for a function of a single variable. There's three of them for a function of two variables, so it's not surprising it's a little bit more complicated. We scroll over to the other page. This first example here is just an example from a one-variable situation, kind of scaled up to two-variable situation. But this is the real interesting part of it here in definition 1.8, where we define stationary point. The terminology critical points is also sometimes used. So these are points. Okay, I'm using x0, y0 there instead of ab, but some kind of base point. They're base points where both partial derivatives vanish. So remember f subscript x, f subscript y, they refer to the two first order partial derivatives. And then they're classified. Now, unfortunately, I'm using D again, but this is a different D to before. They're classified using the second order partial derivative expression D, which is, well, it crops up in other parts of the theory, but it's the determinant of this 2x2 matrix of partial derivatives. That matrix is called the Hessian matrix of the function f. See, it's the second order x derivative and the second order y derivative on the diagonals and the mixed second order partial derivative on the off diagonal. So this quantity D that's used to do the classification of the stationary points is the determinant of that. So it's the second order derivative of f with respect to x multiplied by the second order derivative of f with respect to y, and then subtracting the product of the off diagonal terms, which is the mixed second order partial derivative d2f dx dy squared. Okay, so that's this quantity D, which is the determinant of this matrix, and that is used to do the classification. If the D comes out as negative, that's the simplest one. You see, it's a mixture of second order partial derivatives, so you evaluate it at each of the stationary points. When you evaluate that expression D at one of the base points, if it comes out negative, then that means we're dealing with a saddle point. If it comes out positive, then it will be either a minimum or a maximum, and what it is depends on the sign of one of the straight second order partial derivatives. You can either use the x derivative or the y derivative. Okay, here it's stated it's just using the x derivative. So if D is positive and the fxx is positive, then it's a local minimum. And if the fxx is negative, then it's a local maximum. Okay. And there's an example worked out here, which is example 1.3, where we take this function, f of x, y. It's a polynomial function. Okay, so the derivatives won't be too hard to evaluate here for this example. The x derivative is 3x squared plus 3y squared minus 15. The y derivative is 6xy minus 12. So we're looking to solve both of these in order to locate the stationary points. Now the equation which has the simpler structure is the y derivative, 6xy minus 12. We know that that's true if and only if y is equal to 2 over x. Simply move the 12 to the other side and divide both sides by 6x. We get this condition y equals 2 over x. So the second equation is satisfied exactly when and only when y is equal to 2 over x. Now we're looking for simultaneous solutions. So if we take that solution for the second equation, the y equals 2 over x, and put it into the first equation, hopefully then we'll get some actual solution points out. When you do that, when you take y equals 2 over x and substitute that into the x derivative, we get this equation for x only. It's a polynomial equation for x only, which we can hopefully solve. Okay? So it's equivalent to a quartic polynomial, which thankfully, for the purposes of this example anyway, factorizes nicely. So we get this condition down here that in order to be a stationary point, the y-coordinate must be 2 over x, and the x-coordinate must be a solution of this. Okay? Okay, you can see there's 4 possible x's. There's plus and minus 1 and plus and minus 2. Okay? So the 4 possible x's, when they're put together with this relation y equals 2 over x, that gives us 4 possible stationary points. Okay? 4 possible locations where both those first-order derivatives vanish. Okay? Then the classification is done. So then we assemble this quantity d. So to assemble d, you would have to get all the various partial derivatives, second-order partial derivatives of your original function f. Assemble this quantity d and evaluate it at each of those 4 stationary points. And the classification comes out like this. The ones based on 2, 1, so 2, 1 and minus 2, minus 1, those are local minimum and local maximum, respectively. The other one, where it's x-coordinate 1, y-coordinate 2, and the negative version, that's saddle point. Now this kind of problem is nice because there's an algebraic solution to it, following this one. Then we can also confirm the results by inspecting the particular function. Okay? If we go quickly to MATLAB here. I'll show you. I think I've got it up here already, so I'll show you on this side.
Yes, okay, such that. MATLAB. Okay, I'll just refresh this. I can't see that yet. HDMI.
So here what I've done is I've gotten MATLAB, when it comes up here, I've gotten MATLAB to draw me the surface corresponding to that polynomial function in example 1.13. And it shows you an example of using, well, there's a few different surface drawing commands in MATLAB. But the one we're using here is, I think it's here in the command window.
Oh, this is the command window.
Okay, so the command I'm using is EasySurf, EZSurf. Okay, so that's a simple enough function for drawing surfaces defined by relatively straightforward functions. You give the definition of the function in terms of variables x and y. You give it as a string. So the first argument to the command EZSurf is this string. So it's a string. It's between quotation marks. And then we're just typing out the definition of the function. And you can use standard functions like cosine and sine and standard functions that MATLAB will recognize there. The second argument is an array of 4 quantities, which are minimum for x, maximum for x, minimum for y, maximum for y. Okay. Of course, you can get all that help you can see all that if you just type help EZ_surf, or just find the help information for the EZ_surf command some other way, searching on the web or so on. Okay, so it explains how to arrange the arguments and so on. When we do it there, it should produce us a relatively nice plot of what the surface looks like. And when you're in MATLAB, of course, you can spin the surface around, look at it from various different angles and so on, which I'm sure you're all familiar with. Now, I graphed it there between the limits plus and minus 3. Now, our solution found that these stationary points were at various combinations of the values 1, plus or minus 1, and plus or minus 2 for the two coordinates. You can see here, yeah, there does appear to be this minimum type of point here over at y equals 2, x equals 1, I think. And at the negative version of that, y equals minus 2 and x equals minus 1, I believe. So we have this feature like a top of a hill here, and a feature like the bottom of a depression there. Those are those two stationary points. To find that the saddle points aren't as clear on that view, but if I zoom in on one of the saddle points, yes, where the saddle points were at the point 1, 2 and minus 1, 2. Minus 1, minus 2. Yeah, so in this version of the command, you might be able to see, it's a bit small, but I'm calling the EZ_surf command, and the minimum and maximums I'm giving it are centered at the point x equals minus 1 and y equals minus 2. So I'm just going a half either way from that central base point. So this should be, the surface that this draws should look like that horse's saddle shape here. Okay, indeed it does. When you spin it around there, you'll see that point in the center of the graph. In one sense, it's like a local minimum point. As you go this way and that way, you're reaching higher points. But in another sense, it's like a local minimum point. You come off in this direction, you're going downhill. And similarly, when you go down the back of the surface along that direction as well. Okay. So that indeed does look, that confirms the algebraic work we just did. That confirms that looks like a saddle point. And so these points on these surfaces, they're significant because they're the locations where the function is momentarily stationary, where both of the partial derivatives have vanished. They're the locations where the tangent plane to the surface is the zero gradient horizontal plane. Okay. Now that was the first example, okay, I've only shown you a couple of examples there, one of the Taylor series type problem, one of the stationary point type problem. But when I see you next, I'll be seeing you next week for two lectures on Monday next week. So I'll make sure to do some more good illustrative examples of dealing with those types of problems. And you'll see the ones that I'm presenting you with in the coursework problem when you get that later on today from Stephen. Okay? So I'll finish there for now, and I'll see you next week.